Hello everyone. This is the continuity for R&AC second unit, and this is third video. We were discussing about the properties of refrigerant absorbent mixtures. The solution used in absorption refrigeration systems may be considered as homogeneous binary mixture of refrigerant and absorbent. Depending upon the boiling point difference between refrigerant and absorbent and operating temperatures, one may encounter a pure refrigerant vapor or a mixture of refrigerant and absorbent vapor in generator of the absorption system. Unlike pure substances, the thermodynamic state of a binary mixture in liquid or vapor phase cannot be fixed by pressure and temperature alone. According to Gibbs' phase rule, one more parameter in addition to temperature and pressure is required to completely fix the thermodynamic state. Now, in basic vapor absorption refrigeration system, here it is plotted on P and T. So now just to show the differences, how with the help of property differences they are showing it. Now you have an absorber, generator, condenser, evaporator. Pg is the generator pressure, Pe is the evaporator pressure, QE is heat given absorbed by the evaporator, and in absorber Qg is coming out, and we have after absorption we use a solution pump, and that pump is made to pass through that as a function of a heat exchanger to absorb the heat coming from the liquid coming from the generator through an expansion valve to absorber, and after that, after acquiring some heat, then again we will send it to the generator, where generator starting point, generator inlet, and where we supply Qg. So from the absorber we are sending the solution by using a pump. That pump will pass over a heat exchanger of a liquid which is coming from generator. That's a solution which is coming from the generator, weak solution that is coming from the generator. Initially we have strong solution, and after absorption it will become a weak solution, and Qg is the amount of heat given at the generator, and the refrigerant, we also called solvent, will get separated, and at the stage 5, now that will be sent to the condenser, where it need to be cooled by rejecting the heat to atmosphere. We call it as QC, and that QC is the amount of heat rejected. It consists of QE, QG, both. So combined together must be removed at QC in condensers, and this is the refrigerant will pass through an expansion device, an expander, just like in VCR systems. Like that of in VCR systems, whatever happens, the same procedure takes place, but the thing is only the difference instead of compressor we are having a thermal compressor, an absorbing unit, an absorption system. Thermal compressor is what we use here, and after expansion again it will enter into an evaporator after losing its properties such as pressure and temperature. The refrigerant will become very cool under low temperatures. It will enter into the evaporator, and through the evaporator the heat absorption of the heat takes place from the foodstuff or the other items, and it will become the vapor form, and those vapors will be again absorbed in the absorber. After absorption, ammonia, after absorptions it will become a strong solution, and that ammonia, that strong solution, again it will be moving to generator. At the generator, ammonia vapors will get separated, and that will become a weak solution, and that weak solution again it will come to the absorber through an expansion valve. That is a simple example for VAR is ammonia water solution, ammonia absorption system. Here ammonia works as a solvent, that is a refrigerant. Ammonia is a refrigerant, and water will absorbs it. So ammonia vapor forms will get absorbed by the water in absorber and will become a strong solution. That strong solution will be pumped to the generator. The strong solution is pumped to the generator, and in between we'll have a function of heat exchanger in order to increase efficiency, effectively using thermal power, thermal energy. Anyhow, we need to heat that pumping solution, so we pass it through the tubules of that is coming from the generator towards absorber. So this is the basic thing is what is happening now. Basic vapor absorption refrigeration system. The thermodynamic performance of the above system can be evaluated by applying mass and energy balance to each component, assuming steady flow process. Yes, steady flow process. What do you mean by steady flow? The rate of change does not vary with respect to time. There is no rate, it will not vary. Any time you take, the rate is constant. At any time, at any instant, the rate of flow is at any section is constant. It will not vary. That is steady state. So with respect to time, it will not change. In simple theoretical analysis, internal irreversibilities such as pressure drops between the components are generally neglected. The internal irreversibilities such as pressure drops between the components are generally neglected. To find the performance from the mass and energy balance equations, one needs to know inputs such as the types of refrigerant absorbent mixtures used in the system, operating temperatures, composition of solution at the entry and exit of absorber, effectiveness of the solution heat exchanger, etc. Now, the refrigerant absorbent combinations for VAR. The refrigerant should exhibit high solubility with solution in the absorber. This is to say that it should exhibit negative deviation from Raoult's law at absorber. There should be large difference in boiling points of the refrigerant and absorber, so that only refrigerant is boiled off in the generator. This ensures that only pure refrigerant circulates through refrigerant circuit, leading to isothermal heat transfer in evaporator and condenser. It should exhibit small heat of mixing so that a high COP can be achieved. However, this requirement contradicts the first requirements. Hence, in practice, a trade-off is required between solubility and heat of mixing. The refrigerant absorbent mixture should have high thermal conductivity and low viscosity for high performance. It should not undergo crystallization or solidification inside the system. The mixture should be safe, chemically stable, non-corrosive, inexpensive, and should be available easily. Heating and cooling of we have an example for VAR system, simple ammonia water absorption, vapor absorption refrigeration system. In this, it may be noted that from the above arrangement consisting of heating, cooling, separation, one finally obtains a vapor at state 7, that is rich in ammonia. State 7 is rich in ammonia. To improve the process, rectification in actual vapor absorption refrigeration systems, as rectifying column is introduced between the generator and deflator. Same. This is a simple. This is a schematic of ammonia water based absorption system, refrigeration system. In absorption system, we have an absorber, we have a pump, and in between we have a heat exchanger for improving the efficiency of absorption system. We have a generator and deflator. From the generator you get separated ammonia with water in a proper way, as it is just we have discussed. Evaporator, at evaporator the absorption of heat takes place, and from there it comes to an absorber absorbs the vapors, will become the strong solution, ammonia strong solution, and from there it enters into a generator. From the generator only ammonia will get separated because of QG. Still you will find some more heat, some more escapings of the water H2O into the deflator. The deflator will perform the same function like generator, again will find small heat. Because of that only ammonia will get separated, water again it will come down, it will get deposited into generator, and from the generator the water will come down through an heat exchanger and expansion valve to the absorber. So this cycle will goes on. We call this as thermal compressor, and from here only ammonia refrigerant will get separated to condenser, will come to the condenser, and again at condenser heat rejection takes place. and the process goes on. Like this we get the refrigeration effect. Now there is 2 fluid system, this is 3 fluid system. In 3 fluid system we have ammonia, hydrogen, water, next dissolved ammonia. This is a very important 3 fluid system. In this we have the functions like generator, we have separator, condenser, evaporator, absorber. You have absorber. One is ammonia vapor is there, hydrogen, water and dissolved ammonia. And one more system is steam jet refrigeration system. Here again the basic same principle is the vapors of the solvent, the vapor pressure of the solvent is less than that of the vapor pressure of the solution. Under this principle steam jet refrigeration system works. And at ejector, this condensation takes place at ejector. You will find a diffuser, and this nozzle will send the moving stream, and in the diffuser it will not, the function is different. It will create a high pressure in the diffuser, and because of that to the left side of the ejector you will find low pressure. As a result the vapors move on escaping into up, and at the condenser it enters into the boiling feed. Again it is coming to the makeup water. Now this chilled water, the lower layers in this chamber, the lower layers are chilled water, and this water is used for some different purposes, refrigeration purpose. Thereby this second unit is also completed. And we missed one topic, that is vapor air refrigeration system, that is Brayton cycle, reversed Brayton cycle. In reversal Brayton cycle two adiabatics and two isobaric heat interactions takes place. Just go through it, solve the problems, and thereby we can complete the second unit. And in the next video we enter into the components of refrigeration, that is third unit. The different components like compressor, condenser, expander, evaporator. There are different types, and in that we will discuss all the types in third unit. Thank you.